Stress can cause the material to collapse or rupture. Here are some examples of solving stress in materials. Welcome to Mechanics of Deformable Bodies. The first problem consists of a timber post which is fitted into the grooves of the steel end cap. We are to look for dimensions A and B with the stress capacities of 1.8 megapascal in shear and 5.5 megapascal in bearing. Let's start with the given shear capacity. Tau is 1.8 megapascal, which is the same as 1.8 newtons per square millimeter. Shear stress is just the shear force V all over the area of the crack. Since there are top and bottom grooves of the steel end cap, consider two crack areas. These two areas are caused by the force which is distributed evenly. So each force is then 12 divided by 2, making V as 6 kilonewtons. If we translate the crack area, we have the dimensions B and the timber thickness of 100 mm. Therefore, using shear stress, we will be able to solve for dimension B. Plugging the values into the equation, we get 1.8 megapascal is equal to 6 kilonewtons by the conversion factor of 1000 newtons per kilonewton. This is divided by the crack area of 100 mm times B. B is then cross-multiplied by the stress of 1.8, and B is computed as 33.33 millimeters. Now, using the bearing capacity of 5.5 megapascal, we expect to find dimension A. The bearing stress of a material has similar equation of force over area. The area considered this time is the contact area. Again, since there are two contact areas of the timber and steel cap, we also have to distribute the force. So each groove is affected by F over 2, that is 12 over 2, which is 6 kilonewtons. For the contact area, dimensions considered are the thickness of 100 mm and the height of the groove A. Now we can place values into this stress equation. 5.5 newtons per square millimeter is equal to 6 kilonewton times the conversion factor of 1000 newtons per kilonewton, all over A times the timber thickness of 100 mm. Switch places for A and stress and simplify the equation to have A as 10.909 millimeters. The second problem consists of a yoke system with a pin. We are to look for the largest bearing stress of the system, the average shear stress in the pin, and the largest average normal stress in the members. Analyze the yoke system first. There is one pin, and the two legs are termed in the problem as members. With two members, the force is then distributed evenly, resulting to 25 over 2 or 12.5 kilonewtons in each member. Let's start with the bearing stress between the pin and the two members, with similar equation of force over area. Take a look at the system from the right side perspective. The contact areas considered are those inclusive of the diameter of the pin and the thickness of the members. The bearing stress is then computed as the force of 12.5 kilonewtons converted to newtons by multiplying 1000 and this is divided by the member thickness of 7.5 times the pin diameter of 12.5 millimeters. The bearing stress is then 133.33 newtons per square millimeter, or 133.33 megapascal. The next requirement is the average shear stress, still with the same formula of force all over area. The area considered this time is the crack area of the pin, and there are double shear for the system. Thus, the force is then distributed among the two members. Shear stress is then 12.5 kilonewtons times 1,000 newtons in 1 kilonewton all over the cross-sectional area of the pin, pi over 4 times the square of 12.5 mm. This is then simplified having shear stress as 101.859 megapascal. The third requirement is the largest average normal stress. By the term average, we meant each member of the yoke. Thus, the force is again divided by 2. Normal stress equation is still force all over area, but the area is focused on the member. Take the cross section to clearly see the area. The largest member area is the width of the member less the diameter of the pin. Normal stress is then 12.5 kilonewtons times 1,000 conversion factor all over the member area, taken as the thickness times the width less the diameter. The stress is then 12,500 newtons all over 7.5 mm times the quantity of 25 less 12.5 millimeters, simplified as 133.33 megapascal.